Hey, good afternoon. See, this is working. Yes. Good afternoon. I have some announcements. Just want everybody to pay attention. We're gonna have our second exam on Wednesday, October 27th. That is next week. You need to be aware of that. So our second exam is on next week on Wednesday, October 27th. We're gonna have a review on Monday, the 25th. So the material that we'll be covering today and on Wednesday is going to be part of the exam. For the exam, I'm considering the option of maybe doing the exam online. I will give more information about that in the review session on Monday. Maybe could be a combination of in-class, online. No, I will decide next week. Early next week, but there's a possibility that the exam could be online. What that means is that you'll be taking the exam from home, or I mean, you're going to be using your computer. So make sure that you have access to a computer and a reliable access to internet. If you want to come to take the exam here, you're welcome to do that as well. You can connect to the computer in here, but that's the latest. So it's not official yet, but I'll make the final announcement on Monday. So for today, we started this lecture 7 on Wednesday, on personal requirements, and we talk about different systems that are part of a facility that are there for the employees. So those are systems that you have to provide for the employee. So you provide a better environment so they are safe and also they can perform better. We're talking about different things. One of those things that we learned how to design was the parking lot for the facility, and that I think that was the last thing we covered. So you had a lab for that. Most of you submitted the lab. So is there any questions for that particular exercise? I got one question about whether or not to include the disability parking spaces, and for that exercise we didn't have to. So in the exam I will be very clear on what you need to include or not to include for that type of problem. So for the lab node, you didn't have to consider the disability or spaces. So it was just for standard cars using a specific module, and you were given the area and you were designing for that area. Okay, so to continue this lecture, we're going to talk about design of restrooms, basically discuss the requirements, standard requirements for the design of a restroom within the facility. So in terms of location, restrooms should be located within 200 feet of every permanent workstation. So again, standard measurement. So you have to provide at least one access within 200 feet from any workstation. So that's in terms of coverage. So you can think about the coverage, maybe draw a radius around each workstation, make sure that you satisfy this requirement. The recommended minimum number of toilets or water closets for the number of employees working within a facility is given in table 2. So I'm going to show that in a minute. In restrooms for males, a urinal may be substitute for a toilet, provided that the number of toilets is not reduced to less than 2/3 the minimum recommended. For space planning purposes, this area, 12.5 feet square or 15 feet square, should be allowed for each toilet and 6 feet square for each urinal. Toilets and urinals must be designed to accommodate wheelchairs for handicapped employees as well. So you'll see for most of facilities, like including this building, you'll see that an area is always prepared for wheelchair access. So these are the requirements based on the number of employees and also based on the type of industry. So you can see for these 3 tables at the top, we have the type of industry that we are designing for. So for example, at the top, we have business, mercantile, industrial, other than foundry and storage. So based on the number of employees, you will see that the number of water closets are changing. And also based on the number of employees, you will see the number of laboratories will change. So for example, between 56 and 80 employees, you'll be required to have at least 4 water closets and between 61 and 84 laboratories. And then for 1 additional water closet for each 40 employees in excess of 190. So if you go above this number, you need to make sure that for every 40 employees above that 190, you consider an additional water closet. And you'll see that that also changes according to the industry. So if you look at assembly, other than religious and schools, you have between 100 and 100. You require only 1 water closet. So more people, you don't have to provide the same level as for business. So more people per water closet. And then in terms of urinals, same thing. In laboratories, also same thing. So you don't have to memorize these numbers. You need to be aware that there are different requirements per industry and that the number of water closets in laboratories will be changing according to the type of industry and also according to the number of employees. And if you need to design for this, then you will look at the standards like the ones that I'm showing you here. So this is a typical restroom layout for typical fixture clearance based on New York State Labor Code. So as you can see, we have the lavatories at the top. These are representing the urinals, and these are representing the water closets. We have the dimensions. So you see about 2 feet minimum between lavatories, about 5 feet between lavatories and the doors for the water closets, and Also some same area between lavatories and the urinals. What else? And you have to provide enough clearance for access, right? So here you have 2.6 or 2.5 feet for entering the water closet or the restroom, and then 3 feet and 6 inches for entering the area of the restroom. Okay, so again, general guidelines for the design of restrooms. We can now look at the design of different office spaces. So now we're going to look at a little bit about office planning. You'll see the different type of office layouts that we can consider for a facility, depending again on the number of people that you're designing for. So according by Dr. F. Becker, Director of Cornell University International Workplace Studies Program, the fundamental idea is that people should work under conditions that they can be most efficient. So we need to keep that in mind when we are designing a space, like an office for collaboration. Location and time should be of secondary importance. So he asked, why not create an office where the probability of bumping into people for the exchange of ideas is increased? Especially important now for if you have seen these pictures or if you have visited these areas or these companies like Google, Amazon, you'll see that office spaces are no longer the traditional design. Now you have these big open spaces, you have spaces for collaboration, you have these boards everywhere, you have tables around this open space. And the reason for that is try to keep collaboration, people bumping into each other and develop new ideas. So most important influences on the development of the office design is technology, organization, the building construction, and the real estate package. Office differs from factories in at least 3 ways: the product, the physical environment, and the social environment. So we are no longer designing for a manufacturing of a particular product. Here, we're thinking about people, we're thinking about communication, social environment. So the goal of office layout is to minimize communication costs and maximize employee productivity. So how do we achieve that? There's a combination of teamwork and telecommunications. So now after COVID, we also can add an additional level to this, these virtual environments that are commonly used for communication purposes and meetings. The criteria for evaluation of office layouts are 3 and 4, Suitability in terms of operational effectiveness, flexibility in terms of possibility of efficient change and growth. So can you, if you bring in more people to your facility or to your company, can you accommodate those easily? And habitability, features and facilities to achieve efficiency. Do you provide Wi-Fi in every location of the office space? Or do you have a way to connect your laptops? Or do you have enough lighting for collaboration and work? Do you have space for open meetings? Or you have space for private meetings? All those things are important. Advancement of administrative profession. That state-of-the-art offices planning and design. So there are 3 major type of office arrangements. The first one is the conventional office. Second one is what we call the landscape office, and the third one is the open plan office. So we're going to look at those individually. For conventional arrangement, the defining concept is separate the higher ranking individuals from the rest of the personnel. And the characteristic of the arrangement are, you will see private offices for higher ranks, and then no partitions between desks, no plants, straight lines, and desk only. So when I was an intern 15 years ago, I was working for a financial institution, and we had this type of concept. It was not a very nice environment to work on because you're basically exposed. Everything you do is observed by the higher ranking individuals, which have their separate offices with a view towards where the most of the desks are. So this is what it looks like. You have this open space, everybody's working in here, and then you have the administrative personnel looking towards that area, and they are in their separate private offices. But this is good in terms of communication, so you can see or easy to communicate between desks. Also, you know who's available, who is busy, and so on. Second, office planning in terms of landscape arrangement, defining concept. Officers must be down in with the troops. So here you don't have a differentiation between, let's say, the BP versus the employee. Everybody is located at the same in the same area. So characteristics of the arrangement: no private offices, some partitioning due to furniture, plants, no straight lines, desks, and some storage units. This will be pretty common. I will say this is what you will observe in office spaces in most of the companies. So actually, yes. So you will see something like this. You have desks organized in certain way. You kind of have some private space, but at the same time you are with everybody. So your partition basically is going to be your own desk, and you have space for collaboration. So you will see some crooked paths replace the straightforward aisles and corridors. Desks are arranged in order to minimize communication costs. And then the open plan arrangement, defining concept is the action office. Characteristics of the arrangement is a few private offices, extensive use of partition, plans, straight and curved lines, work surfaces, storage units with wide variety of sizes and shapes. And also very common, you'll see the use of this partitioning. If you go to most of the administrative offices here at the university, you'll see this type of layout. So you have storage around, and you have a space that is partitioned by the furniture. Open plan office is furnished as one integrated office and will be invariable partitioned into smaller offices. The partition itself normally consists of screens, but may consist of solely of plants in pots or stands. And the open plan office generally accommodates staff from different levels and is favored by firms adopting the one-stop shop approach. And you will see that sometimes you will have this type of conference table, which is not separated by the rest of the partitions. The open plan and modular furniture allows for more people in the same area, less arrangement costs, less energy costs, and possibly more productivity. So here's some other examples. So again, partitioning, using furniture, and here is a better picture on showing the open space. You see no large walls, everybody's in the same area, and the only separation they have is their work area desks. Advantages and disadvantages in terms of information: improve information flow, flexibility, democratic outlook, cost and space saving, ventilation, and productivity. Again, this is open space. Leads to promoting poor visual and acoustic privacy. So again, everybody's the same level, not a lot of privacy. So you hear, like if a phone is ringing, you might hear it in your area. Lawful signs of status and control of surrounding by the individuals, and lower quality of office care with related incidents of illness. So for example, you are in a pandemic, everybody's crowded in the same area. So other type of prevention methods should be included. In terms of office planning for special areas, as I mentioned, not only the space for the employee or the employees, but also you need space for meetings, you need space for training, you might need some space for computational, maybe servers and so on. So you might need to look at the different requirements for each of these special areas, like conference, meeting, training rooms, shop, offices, reception area. So for the conference room, use dimension, equipment, furniture, and illumination requirements. Shop offices can be prefabricated with windows that allow people to monitor activity of the factory floor, maybe used sometimes for storage. And the reception area, here's where you have security, number of visitors. You need some access to a phone so you can communicate for people picking up or getting visitors. Access to restroom and furniture requirements. So again, in terms of office planning, from my perspective, it's relevant to understand the difference between the three types that we have discussed and learn about the advantages and disadvantages between them. And then finally, we have the barrier-free compliance, which is very important. We need to make sure that we provide access to everybody within our facility. So you as a facilities planner must be aware that if you are not meeting certain requirements for barrier-free compliance, the facility must face some fines or any other type of repercussion. So it's important to plan for this. In addition that you're providing a better environment for your employees. So facilities planning must incorporate the intent of the American with Disabilities Act. Disabled persons will have the same right as the able-bodied to the full and free use of all facilities that serve the public. A barrier is a physical object that impedes a disabled person access to use the facility. So for example, having a ramp is important for people using a wheelchair. The sidewalks, if you're looking at the outside of the facility, make sure that they are level up, or they have the right inclination so people can go up and down without a problem. That the doors are wide enough for access. If possible, provide these automatic doors that will open for people with wheelchairs and so on. A door that is not wide enough to accommodate a wheelchairs or stairs without a ramp access to a facility are examples of a barrier. So account for the handicapped person space requirements versus of an able-bodied person. So the wheelchair dimensions, reach, and maneuverability requirements are stated here. So we have a typical clearance of 2.3 or 2 feet and 3 inches to 2 feet to 5 inches. And then the wheelchair dimensions and turning radius. So you need at least 5 feet and 3 inches for the turning diameters. And then in terms of reach zone, we need to be aware of the space that we have for reaching. So high reach between 4 feet and 10 inches. A typical is 3 feet and 2 inches, and the low is 2 feet and 7 inches. And the easy reach area is denoted by this gray area right here. Okay, so that completes this lecture on personal requirements. Now we are going to transition to a different topic. So we spent time on talking about the different systems within the facility, talk about designing for physical systems, such as designing for the HVAC systems, and so on. And then we focus on the personal requirements. Now we are going to look at a different topic. We're going back to the scheduling component and how that affects our design. So we're going to look at schedule design. And this is material that is covered in sections 2.4 of your textbook. And this lecture in particular is tied to objective number 2 in terms of learn formulation models and analytical procedures for the study of facilities layout planning. So we are going to look at 3 topics today: the marketing information, process requirement, and the machine assignment problem. And the idea is learn how to plan for some of the equipment requirements into a facility. For example, how do you know how many machines do you need for an area? Okay, so computing the number of machines needed for a particular department or area in your facility. So schedule design decisions provide answers to questions involving how much to produce and when to produce. In addition to how much and when to produce, it's important to know how long production will continue. Such determination is obtained typically from this market forecast. So you're looking at different seasons, you look at your historical data, you use that information to provide or to create this market forecast. And then those forecasts are telling you what you should expect based on your previous performance. So based on those forecasts, you're going to make a plan in terms of what you need to produce for, let's say, next week or next month or the next 2 months. To plan a facility, information is needed concerning the production volumes, the trends, and the predictability of future demand for the products to be produced. So if I'm designing a facility, let's say for Amazon, I'm looking at increasing my capacity for Christmas or for, let's say, the winter season. I look back at how much demand I had last year. And then based on that, I can forecast maybe I will have a 10% increment in the number of orders this year. So if I need to create a new warehouse or plan for a new warehouse, at least it should cover that extra 10% increase that you are predicting for the next year or for the next few years. So that's why we need these production volumes, trends, and the predictability or forecast models for the future demands. And then if you're predicting that 10% increase, then you look at your volume and you can compute how much space you will need. And how is that linked to this lecture? Well, if you know that you're going to be processing, let's say, 10,000 more boxes during December, then you can start planning for, let's say, how many trucks would you need for transporting these extra boxes? Also, how many conveyors do you need to split the shipments? Also, how many people do you need in your facility to help you load these trucks? So the more specific the inputs from product, process, and schedule designs, the greater the likelihood of optimizing the facility and meeting these needs or meeting the needs of the manufacturing. So again, you go through this whole process of forecasting what can happen next year, next month, next week. If you're planning for a new facility, most likely you're looking at long term. So you want to predict for the next 5 years, probably at least. And then based on those forecasts, you are looking at what will be needed for you to be able to accommodate that growth in terms of product, process, and schedule design. So what type of information can we use? Well, it's marketing information. As a minimum, the market information given in table 1 is needed. So here we have information about the product or service that you're providing, and we have 4. And we have the minimum market information. So we start with the first year volume, second year volume, 5th year volume, and 10th year volume. So using this data, you can start looking at the trends for each one of these products, and you can build some forecasting models in terms of what you should expect. So not all of these products are showing a growth. For example, A is showing that growth from 5,000 to 10,000, but B is showing the 0 at the end. So you're still producing in 5 years, in year 5, but then in 3rd year, 0. And then this is kind of constant. And then this one is showing that increasing trend. So for you to have an accurate estimate, you have to look at these trends, these time series, and then try to fit a forecast model for each one of these trends, and then forecast for the amount of time that you want to predict. Obviously, these forecasts are not 100% accurate. So you might have some uncertainty around these numbers. So ideally, you will have information of the type shown in table 2, that you not only have the data for what happened, but you also have some probability associated with the possible outcome. So for example, for product A, we are looking at 3 possible scenarios, and we have a probability associated with each one of them. The most likely obviously have the largest probability, which is 50%, but you also have a pessimistic and optimistic scenario associated with product A. So you see that there's a 30% probability that you will end up only requiring 3,000, most likely 5,000, optimistic 6,000. And that's for the first year. For the second year, same again. You have probabilities associated with this scenario. And you can see how this, as you move forward, your forecast, this goes from 0.5 to 0.6 to 0.8 to 0.9. The most likely is increasing that probability, and the other 2 scenarios are going down. Same thing for each one of them. So why is this uncertainty important is that, again, forecasts are not necessarily 100% accurate. So if you want to have some idea of your boundaries or your lower bound and upper bound in terms of volumes that you should expect, then associating that uncertainty to your volumes is important. So this will be ideal. And then using these probabilities, we can forecast for each one of these possible scenarios and then make a decision that considers that uncertainty. So if such information is available, a facilities plan can be developed for each demand state and a facility design with sufficient feasibility to meet the yearly fluctuations in product mix. Okay, so as we saw, not all the products are behaving in the same way. So maybe in some years, you will have a larger area of your facility being used for product A, and then later, 10 years from now, that space will be occupied by another product. So in addition to the volume, trend, and predictability of future demands for various products, the qualitative information listed in table 3 should be obtained. So these are valuable information that should be obtained from marketing and used by the facilities planner. So here we have 6 questions. And we have also the facilities planning issues impacted by the information. So information to be obtained from the marketing department, who are the customers of the product? How is that impacting your facility? Well, you need to know what type of packaging you should provide. Is this, for example, I know Amazon will provide different type of packaging depending on how much they will charge you. So susceptibility to product changes and susceptibility to changes in marketing strategies. What are the customer, or where are the consumers located? That should tell you, okay, where you should locate your facility or your new facility, the method of shipping. So if your customers are located in an island like Puerto Rico, then you need to be aware that you might not use trucks to get there. So you need to have some type of airplane or ship to go and serve those customers. Seasonality, method of shipping, warehousing, system design. Why will the consumer purchase the product? Is this something that is seasonal? Is this something that is based on price? Or is it based on the type of packaging that you're providing? Where will the consumer purchase the product? Is this something that you buy in unit load sizes, or the processing, or packaging? Those 3 areas. Like, are you going to the store buying this? Are you going to order online? Those are things that are important. What percentage of the market does the product attract, and who is the competition? Very important. Who's your competition? Who you're competing against? Do they have a similar system that will get you, will get them the same type of product, and so on? That will affect your future trends, the growth potential, and the need for flexibility. And what is the trend in product changes? That will tell you how much space do you need, the material handling methods, and the need for flexibility. So very important information that you need to obtain in order to forecast how your facility will look like in the time period that you're planning for. Okay, so let's look at the process requirements. So specification of process requirement typically occurs in 3 phases. The first phase determines the quantity of components that must be produced, including allowances for defective items, in order to meet the market estimate. Okay, so we did that already. If you think about determining the number of parts that needed to go into this process in order to obtain the desired output. That's what we did in the first part of the semester. We considered the defective items, and we computed how many items we needed to have at the beginning of the process in order to make sure that we met these desired output. The second phase determines the machine requirements for each operation. So how many machines do you need in order to make this meet this desired output? And the third phase combines the operation requirements to obtain overall machine requirements. So today we're going to look at these three phases. So the estimation of the number of machines required begins with the identification of the machine used by individual operations. The machine fraction for an operation is determined by dividing the total time required to perform the operation by the time available to complete the operation. Okay, so that will be the machine fraction for an operation. The total time required to perform an operation is the product of the standard time for the operation and the number of time the operation is to be performed. So if I know it takes me 10 minutes to go from point A to point B on the manufacturing line, and I have to do this 100 times, then that will be 100 times 10 minutes. So let's look at this example. If it takes 5.5 hours to process one part, and if the 6 parts are to be made in 2 hours, then it follows that 1.5 machines are needed to complete the operation. Okay, so if it takes 5 hours to process one part, and if the 6 parts are to be made in 2 hours, so basically with that, we have this requirement of 2 hours. Right, and we know that one part will take you half an hour. Right, then you know that a single machine, this is machine 1, would only take you, or you will be only able to complete 4 parts with one machine. So you need at least half an hour of a second machine to complete the 6 parts that are needed. So that's why you will need at least 1.5 machines to complete the operation in less than 2 hours. Whether or not 1.5 machines are actually adequate to complete all 6 parts depends on the following. Are the parts actually being made to the 0.5 hour per part standard time? Is it taking more or less? You know that if it takes a little bit more than 0.5 hours, you will not be able to make 4 in machine 1, right? So if you just deviate a little bit, let's say 0.6 hours for the standard time, you will not be able to have 4 parts being produced within 2 hours in machine 1. So you will need an additional time period, let's say here. Is the machine available when needed during the 2-hour period? Or if it is used by another process, then you will have to wait. Are the standard time, the number of parts, and the time the machine takes known with certainty and fixed over time? That's another question. So again, uncertainty in the process might not necessarily fit what we are planning for. So how do we manage that? So the question is again, are the parts actually being made at to the 0.5 hour per part standard time? This is handled by dividing the standard time by the historical efficiency of performing the operation. So if your machine is 100%, which is unlikely, efficient 100%, then you will make sure that if the standard time is always 0.5, you'll be able to meet that number. But more likely is that your machine is not going to be efficient to the 100%. So you might have a 95% efficiency in your machine. So that will deviate your plan a little bit. Is the machine available when needed during the 2-hour period? It's handled by multiplying the time the equipment is available to complete the operation by the historical reliability factor for the equipment. Is this machine breaking a lot? Is this machine requiring preventive maintenance a lot? If that's the case, then you will have to take that uncertainty into account. The reliability factor is the percentage of time the machine is actually producing. So if you take that machine out for maintenance, that's not going to be part of your processing time. So the reliability factor is the percentage of time the machine is actually doing some production. Are the standard time, the number of parts, and the time the machine takes known with certainty and fixed over time? If considerable uncertainty and variation exist over time, it may be useful to consider using probability distributions instead of point estimates for the parameters and utilizing a stochastic machine fraction model. So this is the type of information or the type of concept that you learn in IE 3320. So if you took IE IE 3320, which is statistics. You should know the difference between probability distributions and point estimates. The difference is point estimate is a value, is a number. The probability distribution considers the variability on those numbers. So for example, typically in order to estimate, let's say, a processing time in a machine, we will gather data and we will plot that information into a histogram, which is what we are looking at here. So that histogram is telling you, this is, for example, 5, 10, 15, and 20. So this is telling you, let's say this is 6. This is the number of times that processing a part took you about 6 minutes. This is the number of times that processing a part took you 7 minutes. This is the number of times that it took you process 8 minutes. This is the number of times it took you to process in 10 minutes, 11, 15. So you get the point. So you get these bars showing you, like for example, here, this bar is the highest one. So this is telling you that most of the time, it takes you 11 minutes to process that part. So what do you do with this? Once you have the histogram, now you can try to fit a probability model into the histogram. So if you remember from IE 3320, for each probability distribution, we have a graph. I don't know if you remember that. So for the exponential, it looked like this. For the normal, it looked like this, and so on. So for each probability distribution, you had a curve. What we try to do with this histogram is to see which one of these curves fit this behavior the best. So for example, here I will say a normal distribution, like I show you that bell shape, is pretty much similar to the behavior that we are looking at this histogram. Okay, so there's software that will do this for you. It will go and say, well, it will look at the histogram and it will say, okay, this is the best probability model. But we typically do that with the chi-square method or with the KS method. If you don't remember those, that's fine. But that's the idea. That's why you need to know probability and statistics, because now you use this information, you're feeding that distribution into your data. And what would be the next step? Now that you know, okay, my processing time follows a normal distribution with a mean of 10 and a standard deviation, let's say normal with a mean of 10 and a standard deviation of 2. How do you use that? Well, the idea is that you forecast, right? So now you can use this model to forecast the processing time of the next part. You take the normal distribution and you generate a random number based on that distribution. And you can forecast as many as you want, right? So you can forecast the next 100 parts. And then based on that forecast, which is based on this probability distribution, you can plan for your expansion. So you might have, let's say, numbers that look like 12, 13, 11, 10, all based on this probability distribution. So what you learn in IE 3320 can be useful in the type of analysis that we are trying to do. And this is not only for facilities plan, it will be also applicable. You can also apply this to many of the concepts that are taught in other courses. I always like to go back to this because I used to think 3320, most of the complaints that I got from students are, you're learning this, but we don't know how this connects with what we are doing as engineers. It's very important when you start thinking about uncertainty, when you move from this deterministic world in which you think everything is fixed, You know, you think that processing time is 5, it's always 5, the machine is always working, the people will always show up. That's not the real world. Real world is that your employee might not show up, your machine will break down, your orders might come late, and all that is uncertainty around the planning that you have to do as an engineer. How do you include that in your planning? Is by using this information. You plan for the uncertainty in the break, how many times the machine will break. You plan in terms of the efficiency of your machine. What's the probability of that machine producing at that rate most of the time? Then you combine out all that uncertainty in order to make decisions. So that's what we are trying to do here. So typically, such models are not utilized, and the approach taken is to use a deterministic model. Okay, so typically, people are afraid of using probability, or people are not sure how to use probability and statistics, so they will say, let's use just a number. Let's use 10 minutes and plan for that. Most likely that plan is going to be changed in the future, because we know that other things will happen. So plan the facility to provide sufficient flexibility to handle changes in machine fraction values. So for example, if you're not taking into account the uncertainty, if your plan at the end is saying you need 5 machines, you might add the 6 machines just to make sure that if something happens, you have extra capacity. So the following deterministic model can be used to estimate the machine fraction required. So again, this is for planning based on your forecast, based on the processing time, based on the efficiency of the machine, the reliability of the machine, and so on. So F is the number of machines required per shift. Okay, so this is what we want to know. We want to know how many machines I need in this space so I can meet the production required for the facility. Okay, so that's F. S is the standard time per unit produced. Q is the number of units to be produced per shift. E is the actual performance expressed as a percentage of the standard time. H is the amount of time in minutes available per machine. So I have the machines for 4 hours, basically. That's what this is saying. And R is the reliability of machine. So meaning that during this 4-hour period, the machine is gonna be available 90% of the time, meaning that it will break down at some point or some preventive maintenance might be needed. So this is the expression that we're gonna use. The numerator stands for the total time required per shift, and the denominator indicates the total time that one machine is available per shift. Okay, so this is machine availability, and this is the total time required per shift. Okay, so let's look at this example, and then we'll have some time to look at the lab. So here we have a machine part has a standard machining time of 2.8 minutes per part on a milling machine. During an 8-hour shift, 200 units are to be produced. Of the 480 minutes available for production, the milling machine will be operational 80% of the time. During the time of the machine is operational, parts are produced at a rate of 95% of the standard rate. So the question is, how many milling machines are required? Okay, so we can start. Again, what we're going to do is just to apply this formula. SQ divided by ER, where S is the standard time, Q is the number of units to be produced per shift. E is the actual performance. H is the amount of time available per machine. And R is the reliability of machine. So S is straightforward. It's a standard machining time of 2.8 minutes. So S is 2.8 minutes. Q is the number of units to be produced per shift. So during the 8-hour shift, 200 units are to be produced. So Q equals 200. H, 480 minutes available for production. So amount of time available per machine is gonna be 480 minutes. E is the actual performance. So this is giving us the reliability. Milling machine will be operational for 80% of the time. So R is 80%. And the actual performance, parcel produced equal at a rate equal to 95% of the standard rate. So this is 95%. So if we substitute those numbers here, we have 2.8 times 200 divided by 0.95 times 480 minutes. So this is minutes. And this is 0.8. This is also minutes. And 2. Okay, so this cancels out. And F equals 1.535 machines per shift. So we typically go up. So that will be 2. You cannot have 1.5 machines. So if you get a fractional number, you will go to the next. Okay. And now let's use the rest of the time period to start the lab. It's associated to what we just did here. Okay, so this is the lab. A part requires 3 processing steps on 2 machines in the sequence ABA. The demand for this part is 10,000 units per week. The company operates 6 days per week, 8 hours per day. Given the following data, find the number of machines needed, of the number of each machine needed to meet the demand. So we have data about the operation, type of machine, standard time, efficiency, reliability, and defects. Okay, so what we don't have here, actually we have demand for this part is 10,000 units. So before we get into finding these numbers, we have to be aware of this last column. In addition to the efficiency and the reliability, we have information about the defects, defect rate, okay, which was not part of the problem that we discussed a few minutes ago. Now we are adding this extra level of defects. Do you remember what to do when you have these defect rates? Okay, so this basically ties back to what we did on the first part of the semester, that we were computing based on the number of defects that you would have per machine, what will be the required input for this process. Okay, so you need to know what's the required input, because if you just said I'm going to plan for 10,000 and you're losing parts in every process, then you need to make sure that you plan for more than that. You need to know what's the actual number of parts that you need to be producing, meaning that input at the beginning of the process, in order to achieve these 10,000. Okay, so I need to know how many parts needs to be produced, meaning number of parts that I need to go through to put through this process in order to get that 10,000 that I need. And I need to take into account the defect rates. So basically what I'm saying is, let's see if I can draw something here. Yeah, I can go through that. Let's see. I go here. So I have this A, the machine, and the machine B. And that is I want to get this $10. But I know that I have A equals 3%. B equals 5%. And BA again. 5%. So the question is, how many do I need here? Because that IA is going to be equal to my Q. Let me make that here. So in this problem, everything is given. The only thing that you have to compute is Q, and Q is going to be impacted by these defect rates. You have A, B, A. These 3%, 5%. These are the defective rates, and 5%. And you need to produce 10,000, or you need 10,000 units, good units at the end of the process. So the question is, what is the input? And that's going to be equal to your Q. So if you, for example, if I call this IA1, say IA1, A2, is going to be the input of B and the input of A2. So the input of A1 is going to be equal to O3 divided by 1 minus D3 times 1 minus D2, 1 minus D1. The input of B is going to be equal to, and this is O3 right here, equals O3 divided by 1 minus minus D3, and the input of A2 is going to be equal to O3 divided by 1 minus D3. So you need the input for each one of them, because at the end, f of B is going to be equal to QB times SB divided by H times EB times the reliability of B. And f of A, or the number of machines for operation A, will be equal to QA1 times SA1 divided by H times EA1 times RA1 plus Q of A2 times S of A2 divided by H E A2 R A2. So for the number of parts or the number of machines that you need for operation A, if you have two stations that depend on A, it will be the summation of the F for A1 and the F for A2. And then I think you have to make sure that you get the right age. So this is for 8 hours a day. One day, you have 60 minutes per week. So this should hours, days. So these results should give you minutes per week. Yes. QB will be the IB, yes. Yes. And QA2 will be IA2. Yeah. You need to compute each one of them. Yes, and I'll let you, I mean, everything you need to do is right there. So I'll let you complete that on your own. And then make sure that you submit by tonight. And we will continue our discussion on Wednesday. So the material we covered on Wednesday will be the last material for the second exam. So we'll go over that on Wednesday, and then on Monday we have the review, and on Wednesday next week, the 27th of October, October 27th, we'll have our second exam. By Monday, I will make the announcement whether or not the exam will be online. Okay? Yes. If it is online, it will be during the class time. So an hour and 20 minutes. Yes. Might give you extra time for uploading, about extra 15 minutes to upload the materials. No. I mean, I can make it an extra hour and I'll make the exam longer. So, so it will work both ways. Now I need to be conscious about your time. I know you guys have other courses, and some of you have another class after this one, so I need to make sure that it's within the time period of the class. Okay, so if you're done, then I'll see you on Wednesday. And if you have questions, now is the time to ask. If not, then I'll see you on Wednesday. Can I disconnect the machine from the projector?